So here's the second part of this section 3.6, and that is related rates. And one of the things that's most important when you're doing these is, if you can, you should really draw a picture. Because it's kind of hard to wrap your mind around what's going on. So you're going to draw a picture if you can, and then you're also going to make sure that you label things really clearly. So in this problem, we have inflating a balloon. So a sphere is being filled up at a constant rate of 2 cubic centimeters per second. So I'm talking about cubic centimeters. Right away, I know that that is related to the volume. So 2 cubic centimeters per second is going to be my dV dt. And we want to know how fast is the radius increasing when the radius is 3 centimeters. So we're going to set this up, take our derivatives, because we're talking about how things are changing over time, right? The radius and the volume is changing over time because it's being inflated. And then we're going to solve for, in this case, we want to know how fast is the radius changing. So we want to find dr dt. Here is the equation for volume of a sphere. And because we are in centimeters, it's in cubic centimeters. So when I go to actually set this up, I should have not used that part because I don't want more stuff in there than I actually have to deal with. So the units we can come back and deal with later. But the formula is 4/3 pi r cubed. And that's for the volume of any sphere. And then just did a little rewrite because we're talking about how things are changing over time. So volume is a function of time, which means I have to use the chain rule on that. And the radius is a function of time, so I'm going to have to use the chain rule on that. So we get v prime of t. When you multiply the 4/3 with that 3 out front, these 3's are going to cancel, so I get 4 pi. And now it's r of t squared, and because the radius is a function of time, I have to do the r prime of t. And then we're just going to plug stuff in. We know that v of t was given to us as 2 cubic centimeters per second. And then we know we have the 4 pi. R of t is what we're trying to find. And we know that's a centimeter squared. R prime of t. And they solve this for v of t, for r prime of t by dividing everything out and simplifying it and then plugging it in. So we wanted to know how fast it was changing when the radius was 3. So they just plugged in 3 here and we get 2 pi times 3 squared is 9. So 9 times 2 pi is where the 18 pi comes in. So it's 1/18 pi centimeters per second. This one I left the units in there so you could see exactly how they kind of canceled out. But a lot of times I wait and put the units in at the very end because you do have a lot of variables going on in there, just so you don't get confused. But you can see again when you divide it out, that centimeter squared knocks out one of those centimeters, and it's a way of justifying what your actual units are. So when the radius is 3 centimeters, it's changing at a rate of 1/18 pi centimeters per second. So again, draw the picture, identify your variables. So they have to give you some givens that you're working for, and make sure you identify what you're actually trying to find. And I have one more example. And here we have an airplane flying at a constant elevation. So the airplane is flying at a constant of 4,000 feet. A man is viewing the plane from a position of 3,000 feet from the base of a radio tower. So that distance, we know that this distance is going to be 3,000, but remember the plane is traveling. So at a particular instant it's 3,000, but that distance x is changing. And then of course the distance from the man to the actual plane, we're just going to call that s, that's also changing. So we want to know if the plane is flying at a rate of 600 feet per second, at what rate is the distance between the man and the plane increasing when the plane passes over the radio tower. So when it's straight over the radio tower, we can see we have a right triangle, and we can use the Pythagorean theorem for that. A squared plus b squared is equal to c squared. So that's how we're going to start off. The x squared plus 4,000 squared is equal to the s squared. Now here, again, that distance that's changing between the base of the tower, between the distance between the man on the ground, that x distance, and the s distance is changing over time because the plane is still flying. So we're going to rewrite this in terms of t, just so we can see when we take those derivatives, make sure we're using the change rule. Keep that in mind that these are functions. Those are both functions of time. So when you take the derivative of x of t squared, you bring the 2 out front, and then x of t to the first, and then times dx dt. When you take the derivative of 4,000, that's just 0 because it's a constant. And then on the other side, again, you get 2 s of t to the first power times ds dt. Well, what they did here is divide both sides by 2, and that's where we get this function from. So the givens, we want to find ds dt. So this is what we're trying to find. When x is 3,000 and the speed of the plane is 600 feet per second. So our problem is we don't know what s is. We can substitute in for 2 of these, but we need to be able to substitute in for 3 of them so we can actually find what that missing part is. So we go back to the Pythagorean theorem and solve for s. So 3,000 squared, because again, that's what x is given, plus 4,000 squared is s squared. Solve that for s. It's a 3, 4, 5 triangle. You wind up with 5,000. Now you can plug it in. 3,000 was the x distance. It was traveling at 600 feet per second. We just found s is 5,000, and this is what we want to know. Well, how is that distance s changing at that particular time? So solve that for ds dt by dividing by 5,000, and we end up with 360 feet per second.